this session. So we're solving, as a recap, we're solving the steady state for this matrix, 1/2, 1/2, 3/4, 1/4, and we're going to solve it by solving this eigenvalue equation. So what do you get as an equation? You get AB, AB is AB times this matrix, 1/2, 1/2, 3/4, 1/4. And that's sort of two equations with two unknowns. So the first equation on the left-hand side is A. On the right-hand side, it's a 1/2 A plus 3/4 B. The second equation says a B on the left-hand side, and on the right-hand side, it says 1/2 A plus a 1/4 B. So that's using the second column of the matrix in the matrix multiplication. And if you just simplify a bit, A is 1/2 A plus 3/4 B. That says a 1/2 A is a 3/4 B, moving the A to the other side. On this side, moving the B to the other side, you get 3/4 B is 1/2 A. So I got an equation, a nice equation relating A and B, but I have the same equation twice. Same equation twice. So I got two unknowns, A and B, but I only have one equation. So that's bad. I only have one equation, really. How can I solve two unknowns with one equation? So maybe somebody can give me a hint. You can either put your hand up or type in the chat. What is the hint? How do you solve it from here? Also, you might be able to guess what the answer is by now if you go back to the original question on Mathematize. Yeah, so Rob in the chat suggested if you choose a value for B, and this is the right way to find the eigenvalues in general. So there is a free variable. If someone says find all the possible eigenvectors, then there's a free variable, and you can get that by choosing a value of B. So I think what you guys are thinking of from linear algebra class, which is very good, which is if the question said find all eigenvectors of eigenvalue 1 of eigenvalue equal 1 for P, the answer is to use a free variable or make B be some arbitrary thing, and then you get the answer let B be free. Let B be free, and then A is going to be A is 6/4 B, also known as 3/2 B. So what you get is that the answer to this question, find all the eigenvectors, the answer is this set. It's the set, say it something like this, 1 and 3/2 times B, where B is any real number. So that's the answer to the question, find all the eigenvectors. It's a one-dimensional subspace. It's a line. It's spanned by this vector 3/2 1. But this is not quite what we want. The question that we actually want is find this particular special vector, right? Find the special. This is the actual question we want. The special probability vector V infinity, which is the steady state probability. This is what the question was. So you guys have the right answer in the chat, but to the wrong question. So you have the right answer to the question, find all the eigenvectors, but we want the special vector V infinity, and V infinity is an eigenvector, so V infinity does satisfy V infinity equals V infinity P, but there's something else special about it, and that will let us nail it down. So yeah, let's take a second to think about it. If you have an idea, you can put up your hand or you can type in the chat. We can also look at the possible answers and see if there's a hint there. Okay, so already from what we've done so far, 1/2, 1/2 is definitely not right. 3/4, 1/4, definitely not right. 3/5, 2/5, that could be right. It could also be none of these. So it's either none of these or 3/5, 2/5. But there's something special that these all have, and someone in the chat wrote that they need to sum to 1. So this is not just any vector; it's a probability vector. And when you start the Markov chain somewhere, later on it's got to be somewhere. And so the special fact we're missing is not only is it true that V infinity satisfies this, but also components of V infinity sum to 1. And that's because they represent probabilities, and probabilities have to sum to 1. You could write this, if you really like linear algebra, you can write this as v infinity times 1, 1 equals 1. And that's because 1, 1 will automatically sum the components. This kind of thing is how computers speak. Computers speak very well in linear algebra speak, so you should get used to thinking of things like this. But in our case, we have this special extra equation that a plus b has to equal 1. And if a plus b equals 1, and also, what was the equation that a equals 3/2 b, if you solve this, the solution is a is 3/5 and b is 2/5. So a plus b, they have to sum to 1, and also a has to be 3.5 times bigger than b. That's the answer, and that is this option in MATH4060. I think I can reveal the answer. Did it reveal it? Display results. And so I guess if you chose this answer, you got it right. Okay, that was the warm-up question on what we did last time on the limiting probability distribution. Any questions or comments about that one? So probably I caught you guys off guard, asking you to do a calculation with actual numbers on a Friday morning, but that was the example. Okay, well, if nobody has any questions about this one, we're going to move on to what we left off with last time, which is a weather model, but a more complicated weather model. And so this was the weather model that didn't just have 2 rules, it had 4 rules. And the question that we left off last time is it a Markov chain? And I'm going to let you guys revote. So I'm just going to start presenting this one. And you can choose your answer. It can be different than last time. It can be the same. Yes, no, or it depends. Those are your possible answers. And yeah, you don't need to think too deeply about it. Just go with your gut on what you think. Remember what a Markov chain is. Try to imagine, is this thing a Markov chain? What's going on? Okay. Maybe I'll start a timer for 1 minute.
Could you elaborate a bit more on what a state is?
Yeah, okay, this is great. So nowhere in the question did it tell you what a state is. So it just said, is it a Markov chain? So I told you there's 2 types of weather. There's rainy and sunny. So that on a given day, it can be rainy or sunny. That makes perfect sense. The rules to go from one day to the next day are given. Nobody in the question used the word state. The word state is not in the question. And yeah, you need to think about that. What that means.
Just in general, could you just explain like what a state is for a Markov chain a little bit more?
Okay. So I think it's like a state is just like an abstract thing that the Markov chain switches between. And so a Markov chain, by definition, it's a thing that has states. So like the states, it's like a what's the word? It's like a self-referential definition. A Markov chain is a thing with states. So the question is, what is a state? The answer is it's the thing from the Markov chain. And it just it represents any kind of situation that the thing you are trying to examine could be in. So if the thing you are trying to examine is weather, then it's something like rainy, sunny. If the thing you're trying to examine is a robot, maybe it's like the direction the robot is facing. And so I think it's a really abstract thing that is totally, completely different from problem to problem. And it's whatever the Markov chain is moving between, that is the state. I don't know if that answers your question, Robert, or not.
Yeah, that's perfect. That makes sense. Thank you.
And I think you're getting to exactly what the heart of this problem is. So let's see what people said when I reveal the answers. I have to zoom out a bit to make it. View responses. Okay, here we go. Completely split. So 6 people think it's a yes, 7 people think it's a no, and 6 people think that it depends. So either, there's something weird is going on here, right? Like the whole class, a third of the people think one thing, a third of the people think the other thing, a third of the people think the third thing. We're all completely split. So I think all answers are kind of right and kind of wrong. One of them I think is the most correct. But maybe in the chat someone wants to say like why they think what they chose is right, or we can have a little discussion. You can put your hand up and sort of defend your position. I think yes and no are both valid answers, or they could be valid answers. So maybe somebody who picked yes or no. Let's save the it depends people, because they're kind of like not picking a side. But if you picked yes or no, maybe you can put your hand up and tell me why. Alex, go ahead.
Okay, this is gonna sound like really confusing,
Yeah.
but I think the answer is yes and no,
Okay.
depending on how you think of this problem.
Okay.
It could
Okay.
be,
Go ahead.
yes, this is a Markov chain, because if we're doing what we did with the 7-day forecast, we can theoretically think of past events as being present events at the time, and then we
Okay.
kind of predict the future.
Okay.
But it's also not a Markov chain because we're looking at the past when we typically only look at the present to predict the future.
Okay. I really like that. So you're saying, look, it's kind of like a Markov chain. We can still make predictions about the future, and like that was the thing we were using the Markov chain for. Like we could still do that for this. So it fits into our like mental framework of what a Markov chain is. But the other thing I think you said, which is really good, going back to the very first thing we did in the class, is the definition of a Markov chain, all the way up here in the notes. Let me find the definition. The definition of a Markov chain. Where is it? The very first thing we did. We said a Markov chain has 3 ingredients. It has a state space. You have the sequence. The sequence definitely there. That's what you're talking about. And it has this Markov property that the future only depends on today. And it doesn't satisfy that. So it doesn't have this Markov property, this four rule guy, 4 rule weather doesn't have this. So to predict the future depends on not just today, but also yesterday. And so it's kind of not. Okay, that's great. David.
Yeah, I thought of it as the fact that since we defined future, present, and past, if we define the present as X naught, for example, we know what the weather pattern was like, and then X1 depends on what that weather pattern was in X naught, and then it continues on from there versus just the day by day, because we define what defines the future, the present, and the past in our own terms.
That's great. Okay, so I think you guys are starting to figure out the secret to this problem, and the way to formally say what it is exactly to do with what is the state space. So the question is deliberately kind of misleading. Like over here, I'm using provocative words like future, present, and past. And we have a problem with future, present, and past, right? We have days in the problem, this like weather problem. We know what a day is in the problem, and I'm talking about future, present, and past in the Markov chain. But the thing we haven't said, and the key thing you need to connect everything, is what is the state space. So I sort of like, by trying to skip over what is the state space, the very first ingredient of a Markov chain, you get this incredible confusion. Is it a Markov chain or not? So I think the most correct answer is that it depends. That's what I put. So if you picked yes or no, you probably have the right answer because you're thinking of a particular it depends. So I said it depends. And what does it depend on? It depends on what is the state space. So until somebody tells you what the state space is, the question, is it a Markov chain, doesn't make any sense. You got to tell me what the state space is, and then I can decide. We can look at the sequence of things from the state space, and we can decide. So let's look at this problem. I'm going to scroll back down to the very bottom of our week 1 file. So we have a weather model with 4 states. 4 rules. And the rules tell you about if it's rainy or sunny 2 days in a row. This is example 4.4 in Ross. And this 100% depends on, is it a Markov chain? 100% depends on what is the state space. So is it a Markov chain? And in fact, the question, is it a Markov chain, is always a trick question. Like whenever you see it, really in the wild. And the only way it's resolved, and it's not a trick question, is if people are somehow implicitly thinking of what is the state space. So it depends on the state space. Depends. On the state space. And I think this is a really, really important idea. So, and there's 2 possible things you can think of. the most obvious thing is the state space should be rainy, sunny. This is what we did before. And it's just the weather on that day. The weather on a given day. Okay. So this is one possibility. And if you choose this as your state space, now the question, is it a Markov chain? That makes sense. We're saying we have this thing with the state space, rainy or sunny. We're thinking of the sequence of the weather on given days. And the question, is it a Markov chain, is exactly the same question as, does it satisfy the Markov property? And in this case, the answer is no. This does not satisfy the Markov property. So if your state space is just rainy or sunny, then this model, the rules that were given, they violate the Markov property. The Markov property says to determine what happens tomorrow, you only need to know what happens today, not yesterday. And the rules definitely don't have that. So if you pick rainy or sunny as your state space, that's not enough information to decide what is the probability distribution of the next day. And therefore, it doesn't satisfy the Markov property. And therefore, it is not a Markov chain. So this is, in this possibility, the answer is no. So if you selected no, and you were thinking of this, that's a good answer. There is another possibility. I think David said it, actually. So this is another possibility. David, did you tell us what you thought the state space was? I think you briefly mentioned it. You thought of a way to make it work.
You get to choose what it is. So let me pull it up.
Yeah,
if you choose it's rainy, and then if you choose it's rainy, and then sunny, and then sunny, rainy, and then sunny.
Okay.
As
And
your
so what do
possible
these
states.
what do these things represent, right? So these are two things. So this is kind of like what happens on 2 days. So how do I make the, like, you know, thinking of weather in real life, how do I map it to one of these 4 states? So over here in the easy one, it was the weather on a given day. Now what is it?
All possible combinations of the weather of the last 2 days.
That's right. So it's the combination over the last 2 days. Combination.
Sorry to interrupt, but shouldn't the last one be sunny?
The last one should be sunny. Yeah, thank you. Yes. Sunny. Okay. And this is going to represent what happened on the last two days. Okay. And so I think the way, at least in my brain, that really clarifies what's going on here is you can think of the weather is actually a sequence of letters R and S. So it's like a really long word. It goes like R, S, R, S, R, S, R, ... and it goes on forever. In the original situation, what we were saying was that the state is just whatever it is in one spot. So we said X0 is this letter, X1 is this letter, X2 is this letter. This was our original 2-state model, RS model. X3 was that letter, and so on. So we're just doing like the most obvious thing. Whatever it is, whatever the weather is that day, that's the state. In this new model, this new state space, we have 2 things. And so what we're doing is we're not just looking at one day, we're looking at 2 days that are next to each other. So I think the best way to think about it is you can think of underlining not just one guy, but 2 guys. So the state X0 is not just what's happening on a single day, but it's what's happening on 2 adjacent days. So X0 could be RR, and then X1 would be RS, X2 would be SR, and so we slide this window over day by day. And if you know what happens on 2 days, the rules of the game, for example, if you know it's SR, the rules of the game tell you the probability of what happens the next day, and we can use that to figure out what's happening in our Markov chain on this 2-state space. So if you make this your state space, this is the state space, the new state space. State space with four states, and the states are RR, RS, SR, and SS. Now I think it makes sense. And the rules of the game tell you the probability of the next thing in the sequence, and you can use that to figure out the next thing in your Markov chain. And so with this state space, it really is, yes, it is a Markov chain. Okay, so in a second, we're going to write down what is the transition matrix and make sure we understand the details. But I think this is possibly the most important idea in Markov chains. Everything is a Markov chain if you make the state space big enough. So we said Markov chains, they have this idea that they only look one step ahead in the future. But the thing is, you can cram all the information that you could possibly need. You could cram that into the state space, make the state space some huge thing, and then everything is a Markov chain. And so in real life, when you actually go to solve a problem, coming up with what is the right state space to model this problem is like the heart of the problem. So, if you have a robot and you're trying to like figure out how to train it to do things, what is the state space? Maybe the robot needs to have a memory of what it did a second ago, so it doesn't repeat that. Well, then you better include the memory of the robot as part of the state space. Maybe the robot needs to know if the person controlling the robot ate lunch that day, because that will affect like how it interacts with the person. Then you better include that in the state space. And so I think this is the easiest possible example we're doing now, where you can see that enlarging the state space makes something that wasn't Markov into something that is Markov. And in general, this is a really complicated idea. So like the guys that like beat Go they made an AI for Go, a lot of their time was spent on saying, what is a state? Is a state just the board, or is a state also the board plus the last 10 moves? And I think that is what they decided on. So those computer programs, they input the state of the board, but also what happened in the past. And so that is all included in one thing called a state. So it's really important you don't mix up state of the Markov chain with state of anything else, like rainy or sunny on a given day. Okay, so we're about to figure out the transition matrix for this Markov chain, which is going to be a 4x4 matrix. There's 4 states. But before that, any questions or comments about this idea of enlarging the space? So I'm going to trust that everybody who picked yes or no actually had one of these in mind and got the right answer. But yeah, feel free to ask if something is unclear at this step. And I will, to motivate you, the second question, problem 2 on the first homework assignment is basically a complicated version of this that you have to do. So if this doesn't make any sense to you, you're gonna have to learn it anyway when you do the project. Okay, so yeah, again, feel free to put up your hand anytime, and I'll stop at a convenient time, or you can write in the chat if you have any questions. But let's do this. What is the transition matrix for this guy? What is the transition matrix? And it's going to be a 4x4 matrix, and it has because there are 4 states. If you label the rows and columns, you can label them with the names of the 4 states. So you could say that goes RR, RS, SR, and SS. You could do RR, RS, SR, and SS. And remember, the rows tell you where you are coming from. The rows are the from part, and the columns are the to part. So the columns tell you where you're going to. That is why the sum of every row is always 1, because if you're coming from RR, you have to go somewhere. So the sum of the entire row better be 1. So now we can fill this in using the information given in the question. So let's fill in the question. Let's read the question carefully and fill this in. So if we're starting in RR, that's the first row. If it rained for the past 2 days. So rule 1 is telling us what's happening in row 1 if you started with RR. Then it will rain tomorrow with probability 0.7. I guess that means it's going to be sunny tomorrow with probability 0.3. So there's a 0.7 and there's a 0.3. So it's going to rain tomorrow. Okay, and there's a 0.7 and a 0.3. Problem, I got 2 numbers and I got four things to fill in here. So I know the numbers 0.7 and 0.3 are going to go here, but which ones do they go into? Which ones do they go into? And this is like a bit of a weird hang up. Like, I know it's going to rain tomorrow, but if it's going to rain tomorrow, does that mean that it's, RR? Or does that mean it's going to be SR, or which of these is going to be? And you have to remember, again, the crucial detail is how does raining on a given day translate to the state of the Markov chain? And so I think the key thing to look at is the sequence of letters. So there's, when it rains tomorrow, we know we started in RR. If it rains tomorrow, that means the sequence will have been RRR. So with a 0.7% chance, or 0.7 probability, the sequence will be RR, that's what it was already, and then another R. With a 0.3 probability, it's going to be RRS. So it's going to be sunny tomorrow. And so we're going from the state RR, that's what it was on day 0, or I should say x0. Do not mix up time in the Markov chain and time in real life. x0 was the state RR. We're moving from RR to RRR, and that will be the state. Let's do it in green. The state x1 is what's happening on the next 2 days, x1. So on days when it rains, the state goes from RR, that's what it was in purple over here, to the state RR. And that happens with probability 0.7. 0.7. So 0.7 definitely goes there. With 0.3, with probability 0.3, it becomes RS. And that's because the S on the last day gets tacked on with the R from the previous day. So it becomes RS. 0.3. Okay. And it occurs to me that actually, the way I'm doing this, reading these underlined, perfectly valid and will totally work, but is very slightly different than what is being done in the textbook. So in the textbook, I think they record it the opposite way. So they say that I'm saying RR means RR appears in the sequence. In the textbook, they have it the opposite way, where they say the first one is the most recent day. Most recent day. And this one is yesterday. Yesterday. This is the textbook. The textbook way. Versus my underline way. My underline method has the reverse. So R is yesterday, and R would be the most recent day. And it makes a difference for this RS. So when it's RR, of course, there's some symmetry, and it doesn't make a difference. But you got to pick one and be consistent. So in the interest of being consistent, I'm going to do it the textbook way. And so let's throw out my way of doing it and get everything right. So we're gonna, and you have to specify what this means. And I didn't do a good job of saying it. So I wrote before what happens on the last 2 days, but I didn't tell you which of the two things meant which day. And so now I'm going to be crystal clear with doing it to match the textbook. I'm going to say the first letter is the most recent day, and the second letter is what happened the day before. So when you do this underlining method that I'm doing here, you have to reverse them. So x1 is actually, it's either RR or SR, because you take the last 2 days, but you write them in the reverse order. So I really shouldn't put a 0.3 in RS. It should be in SR to match the textbook. Okay. Hopefully that made sense. So I apologize for kind of getting it mixed up. And I think this is another good lesson that, you know, when you specify things, you got to specify them precisely enough that things actually make sense. And we kind of glossed over that. We said it's the last 2 days, but we didn't specify the order. Now I'm telling you the order. Okay, so for example, maybe I could do an example. The state SR means sunny today, rainy yesterday. Okay, so sunny today, rainy yesterday is SR. If we're in state RR, that means that it was rainy for the last 2 days. The next day could either be sunny or rainy. So we go into the state either sunny today, rainy yesterday, or rainy today, rainy yesterday, and that's 0.7 and 0.3. There's a question. I have 2 numbers, but 4 slots. What goes into these other slots? So what is the probability to go from RR to SS? What is that probability? That's 0. The number that's going to go here. Yeah, someone yelled it out. Say it again.
0.
0. Why is it 0?
Because it was rainy for the past 2 days. Whether it rains tomorrow or is sunny tomorrow, there's no possible way that you can have 2 sunny days in a row.
That's exactly right. So you can think about it like that logically. If you like the sequence of letters, you can say like, how could it be that there's an SS here? There can't be an SS in the green underlined thing because we know for sure that this one is an R. So there's no possible way to get a state that has an S as the second thing, the thing that happened yesterday. And so the probability to go to that state is just 0. 0. Okay, that's one row. You can do the same thing with the other rows. And to say in the interest of time, I'm going to do them a little quickly. So if it rained today and not yesterday, that's the state RS. Rain today, sunny yesterday. It will rain with probability 0.5. So the sequence will become I guess it rained today and sunny yesterday. So this is today. This is yesterday. Then it will rain with probability 0.5. So that we either do RR, SRR, or we do SRS. So we go to the state RR with probability 0.5. If it rains, we have an RR. It's rained 2 days in a row. And if it doesn't rain, because it rained today, we go to the state sunny, rainy. So 0.5, 0.5. And again, it's impossible to get these ones because we know for sure that today is rainy, so we can't go to a state where it was sunny yesterday. So that's the first two. In the next two, very similar idea. Let's do SS first. I think that one's the easiest. If it has not rained the past 2 days, so it's been sunny for 2 days in a row, then it will rain tomorrow with probability 0.2. That means it's going to be sunny for 3 days of sun in a row with probability 0.8. And it's going to be rainy sunny with probability 0.2. And the other two are 0. And finally, rule number 3, if it rained yesterday, not today, that's SR, then it's going to rain tomorrow with probability 0.4. That takes us to a rainy sunny state, probability 0.4. And rained yesterday, but not today. So it didn't rain today. Sunny, sunny with probability 0.6. So this is the matrix, and I think this is the matrix that appears in Ross as well. Okay, so I think this is a good example of how you can take something that doesn't look like a Markov chain. If you make the state space big enough and include the right things, you can think of it as a Markov chain. And you could draw the picture and so on. You could compute the probabilities, the transition probabilities, all the things we did work. And you have this extra difficulty of having to translate between what is the actual state space of the Markov chain and what is you really want out of the problem. So for example, the prediction problem of what is the weather on day 100 or day 7, that's again, you're going to have to do some interpretation of how you translate from these 4 states to whether or not it's rainy or sunny on a given day, because they're not exactly the same. Before they were, but now the state has some kind of double information of the weather on 2 days, and the question only has the question about 1 day. So you got to make sense of that. And this is exactly what you guys have to do in problem 2 of the project. The project is finalized now, and problem 2 is exactly a complicated version of this. So you have to think about it. You have to make a computer program that does the 7-day prediction problem for a general 7. So instead of 7, it's n. And you can definitely do it now. So if you go and think about it this weekend, I think it's a good idea to come with any questions next week. I'm going to do office hours, I think, while we're online. I'll do them immediately after the classes at 12:30. And then hopefully when things go back to in person, hopefully we'll have a change. But for next week, they'll be online right after the class. So yeah, definitely take a look at the problems. Problem 1 is going to be just simulating a Markov chain. So that's like what I did with the dice. You have to make a digital version of the dice and simulate a Markov chain. You can definitely do problems 1 and 2 from the project right now. Okay, let me see. Did I need to say anything else about this one? It's a good time to ask me any questions. We're going to start. I'll just start the next topic that we're going to do, which is sort of leading us into thinking more about how to start training things, how to start doing like AIs and stuff. But this is a good time for questions about this. Okay, so let me start the next topic. So this was, how do you take a problem and turn it into a Markov chain? Sometimes the state space is complicated. The next thing we're going to do, we're going to start layering more and more things on top of these Markov chains. We are going to do a Markov chain with rewards. So before it was a Markov chain, it was rainy or sunny or whatever. It's moving around between the different possible states. And you just sort of watch it and you can calculate probabilities and things like that. But we're going to add on an element called rewards. And we're going to think of, some events as being good or some events as being bad. And we're going to calculate what is the total accumulated value of different things happening. So a Markov chain with rewards is just a Markov chain plus some notion of a reward. And a reward is a real number, could be positive or negative, at every location or step. And so I'll give you the best example. And this is called the gambler's ruin problem. Imagine you're a gambler and you go to a casino. Your starting money is some amount. So you start with N start dollars. And you are going to go to the casino. You're going to bet on coin flips. So your amount of money can go either up or down. And you're going to bet on coin flips until one of two things happens. Either you go broke. So you bet until you go broke. And if this happens, you get no reward. You're sad. Maybe you could say you get -1 reward. We'll say the reward is 0 if you do this. So the number of reward you get if you go broke, you get 0 points. You have to stop gambling, and you're a sad person. The other thing that can happen is you can reach some target, or until you reach some target. Let's call it N target. And if you reach this amount of money, if you ever get to N target dollars, then you are happy and your reward is 1. And so what I've described for you, a gambler who is gambling, maybe I'll be more specific on what the bet is. You bet $1. You bet $1 and you win $2 with probability 1/2. And you win nothing with probability 1/2. So they're fair bets for $1 each, either going up. Your bankroll either goes up $1 or down $1 at every step. Everything is just a Markov chain, right? Where you start at some dollar and some dollar value and start, you go up or down 1 with probability 1/2 for each. And you do this until you either go broke or you reach some target. But we're layering on this new idea of the rewards. So if you go broke, you get $0. If you reach the final N target, then you get $1. Or not $1. The rewards are different than dollars. These are life points. I'm gonna call them life points. So you get 0 life points if you're broke. And you get 1 life point. These are the things you actually care about. So in this situation, like the gambler doesn't care about money at all. All he cares about is life points. And the question is, and this is always the question we're going to answer. Can we find the value of the expected value of the rewards? Okay. So hopefully the problem is clear. We have this gambler, his bankroll is going up and down, and we want to know not something about his dollars, but something about his rewards, his life points. The other way you can see this problem, instead of thinking of it as a gambler, another colorful way people think about it is called the drunkard's walk. So instead of imagining a gambler at a casino who starts with N start dollars, you imagine that there is a drunk guy who is N start meters away from a cliff. And every second he either steps towards the cliff or he steps away from the cliff. And if he gets home, then he's alive and he has 1 life point. But if he falls off the cliff, then he dies. So I'm going with the gambler's ruin. But if you like the drunkard's walk instead, you can call it that. Either way, it's the same problem. And it's the same idea of we have the rules for the Markov chain. Those are explained to us. And we want to know some sort of like a macroscopic quantity, some like long-term situation based on what happens sort of at the end of the Markov chain. So the way we're going to solve this problem, we are going to first set it up as a Markov chain. And then we are going to find the expected value of the rewards somehow. So that's what we're going to do next time. I will say the other thing that maybe should spring to your mind if you've taken a stats class recently is whenever you have a question like this, you have some random variable reward. Reward is a complicated random variable that depends on what happened in the Markov chain. So, it's some maybe complicated process that gives us reward, but you can simulate it. So one way you could estimate the expected value of the reward is to run what is called a Monte Carlo simulation, which is extra appropriate here because it's a gambler and we're doing a Monte Carlo simulation. Monte Carlo just means in science, Monte Carlo just means do some simulations. So one of the ways you can find the expected rewards, method one is run simulations and average them. And there's going to be other methods, but this is a good place to start with. And so I have some code here that does just that. Okay, let's see. So here's the details of the random walk. So this is explaining what the Markov chain is. So this is really just the simple random walk was the first example of a Markov chain that we did in this course. It can go up by 1, it can go down by 1, and those happen with equal probability. We're adding in 2 special rules, which is that if you are out of money, you can't bet anymore. So if you ever get to 0, you're stuck forever. If you ever get to end target, then you're done the game. You just stop there. And the question is, what is the expected value of the reward given your starting point? And so the one thing you can do is you can simulate it. This is what I'm calling the naive Monte Carlo method. Monte Carlo means random. Naive means I'm just doing it in the most obvious way. And what I'm going to do is I'm just going to run n samples with a for loop. I'm going to loop through n simulations of the random walk. And what does the random walk do? It goes up 1 or down 1 at every step until you either reach 0 or you reach the target. And if you reach the target, then you get a total reward of +1. I add this up, I do a for loop over n samples, and then I return the total rewards from all the different runs divided by the number of times I sampled it. So that's what I call the naive Monte Carlo. And if you run it, you can run it with, so I'm doing these numbers, 10, 5, and 100 are telling you the target, where the gambler is aiming for, the gambler's starting money, and the number of samples I'm running. And if you run it, you get lots of different random answers. So here I got 0.44. So the expected reward is 0.44. You run it again, you get 0.53. You run it again, you get 0.51. And so the conclusion is, you have an estimate, but not exactly what it is. And the very first thing you should do is try to improve this a little bit to say, okay, 0.47, but like plus minus how much? Like how close are we really? And that's what we'll do next time. We'll pick it up. We'll learn some better Monte Carlos, and then we're going to learn how to do the real answer using the transition matrix and so on. Okay, so I'll stop there. You should definitely check out problems 1 and 2 from the project. Everything is on the course GitHub. The problems are finalized now and posted as well. Okay, so that's the end of lecture, but I'll stick around for questions. Yeah, Alex, go ahead.
I just have a question about us opening the code in Colab.
Yeah.
I think I tried to do this earlier this morning, but are we able to fool around with the code and adjust the parameters in it?
Yeah, absolutely. So it's on GitHub, and so there's a button in GitHub that says Open Colab, and when you open it, I believe you can make changes and you can run anything you want. If you try to save it, it'll say you need to make your own copy, and then you'll.
Okay, that's what I was worried about.
Yeah, but so I think it's set up so you can't mess it up. So feel free to just mess up. You can change whatever you want, and you can save your own copy in your own, either your Google Drive or your own GitHub, however you want to do it. Yeah, and I will say there is also a template for the project now. So if you go on GitHub, and that one's blank, but has the right spots for you to write your answers. And so that one definitely you should copy and make changes to.
Yeah, you won't screw it up unless you just commit the changes on Git, which would be bad.
Yeah, and I believe since it's my GitHub, I would have to approve it, right? I'm not.
Yeah, you'd have to approve it.
Right. Yeah. So you can try to commit the changes. You make changes and say I want to push these back to GitHub. Don't do that. And you know,
Okay.
if you did it by accident, I'll deny your change. So it'll be fine. But
man.
yeah, feel free to make any changes you want.
Okay, thank you.
Yeah. Any other questions or comments?
Well, I'm just a little bit interested. I watched the AlphaGo documentary, and you mentioned
Mhm.
how they programmed the AI model to play Go, and we were
Yeah.
talking about how you can consider state spaces, that are as large as you want.
Right.
So how would they? And if they considered the last 10 moves,
Yeah.
how would they? I think, well, obviously, finding like all of the probabilities and creating a transition matrix,
Yeah.
like manually by hand would be, probably impossible.
Right.
So, how, if like, how would they approach that?
Yeah, so this is exactly where we're going in the course. So I think we like what we're going to do in the next few weeks is we're starting with like what is a Markov chain and like really hands-on what is the matrix. But basically in real life problems the matrix gets so big that you can't actually decide what the actual matrix is. But you can still do things. For example, like with the very first thing we did in class today, we solved for the equilibrium, and that was this equation. V infinity is V infinity times P. And so one way to do it is the way we did it. You write out the whole matrix. But you can also just sort of treat this as a bunch of equations and sort of solve the equations. And that is like one way to get around writing down the big matrix. And there's going to be an equation, a really important equation, which is very similar to this equation called the Bellman equation. And that is where we're going to get to hopefully next week. And the Bellman equation is a lot like this, similar to the Bellman equation. And basically, you find programs that solve the Bellman equation like little by little. So by playing lots and lots of games, you sort of like improve your solution to the Bellman equation little by little, and then eventually you find the answer. So instead of just solving it directly like we did, there's kind of like a trick to sort of get around it. And again, yeah, you're right. Like you don't write down the big matrix. Yeah, I'm not sure if that really answered the question or if just made it like vague and like pointed to other things.
No, that makes sense. Yeah, I'm looking forward to learning about that.
Yeah, so yeah, I mean, you can try reading the Wikipedia page for this Bellman equation and see what it is there. It's extra hard. In so far what we've done, things are also somewhat easy because there's no decisions to be made yet. So when you're actually playing Go, it's not only is it a Markov chain for maybe what will happen if you think of your opponent as like being some like random entity, but like it's not clear like what are the probabilities because it's not actually random. Like he's making decisions. So there's this extra layer of like getting rid of like how do you take the actual actions that are being played and turn that into randomness. So that's another thing we're going to have to do to get to where we're going.
I have another question.
Yeah, go ahead.
I think it's at the bottom of week. I think it was the Jupyter notebook you had open today in class where we're actually writing out the transition matrices.
Okay.
So currently our transition matrices are like kind of really small in terms of the grand scheme of things. As we get like bigger and bigger transition matrices, are we gonna have to know how to do like sparse arrays?
So I mean, I think this is one way you can extend a little bit the range of possible things you could do. So it's true for Markov chains that have like, on the order of hundreds or maybe even thousands of states. It's all fine. You can put it in the computer as a big matrix. For Markov chains that are bigger than that, they start to not fit in the computer. And one way you can like extend the like window of like possible things that can fit is to do this like sparse stuff. And then the other thing that we're eventually going to get to is we're going to take the equations that come from like what it would be and just focus on just the equations. And then you won't ever need to actually write down the matrix. So sort of like thinking about the matrix will like help you set up the problem and like solve the right thing, but you never actually in your computer program need to say the matrix is this.
Okay, so like, would we hypothetically have to use matrix vector form?
So you will have to use matrix vector form, but not for the matrix, which is the transition matrix, but there'll be other like matrices and vectors. And a really good example that we're gonna get to hopefully soon is that suppose you wanted to do a bunch of simulations. Instead of doing simulations one at a time like I did today with a for loop, when you do a for loop, the computer has to wait until the previous sample is done to do the next sample. And so a faster way to do it is to do everything in a big vector. And it's something like 40 times faster. That's what we're going to get to next class. Eventually at the end of this document is the parallel version. And you can see the times are a lot better. Yeah, here it is. So if you do it the parallel way, it takes 1 second. And if you do it the for loop way, it takes 33 seconds. So that's the real reason to learn vectors and how to do everything with vectors, is because it's a lot faster.
My final question, does my computer have to be like super beefy to
No,
still
so
be able to do most of this?
I'm trying to make it so you can do the entire course on Google Colab. And when you hit the play button on Google Colab, it doesn't run on your computer. It runs on Google's computer. So as long as you have a web browser that allows you to press play,
Okay.
it should be fine. And yeah, that's the goal. There's another site called Kaggle that has more computing if we like run out. But that's my plan for the course. So you shouldn't need a good computer at all.
Sweet.
Yeah.
Thank
great
you.
questions.
Have a good rest of your day.
Yeah, take care and have a good weekend. Okay, anybody else for questions? Okay, so if you are taking the graduate version of the course, stick around and we'll chat a little bit about that.